Metallurgy lab. So in the metallurgy lab, what do we do? Study about metals, structures. Different types. How to identify? Yes, and
how they react with other elements.
Not exactly. How we react, how the metals react with other metals is something which we can't study here. Inka? Yes. To understand the phase diagram, there are various phase changes and other things. Yes, right. And bonds and all is not possible to study here, but some properties, yes. And also we are going to study about the processing of it, meaning there are certain processes that we do to enhance the properties of a metal, right? Like some heat treatment process, even that we can study here. So this metallurgy lab basically consists of physical metallurgy. I already mentioned that physical metallurgy we are going to do. We are going to study about the physical metallurgy aspect, and then we also going to study about some of the major important property enhancements that we do. Okay, so as a part of that, first let me tell you about the list of experiments. Okay, so first thing is to understand the process of doing this laboratory experiment. So that is not counted as an experiment, but it is there as a mandatory, and this is first experiment. Okay, with the 0th experiment we can say. We don't give any number to that. So that is the introduction to metallurgy lab, specimen preparation for metallographic examination, study of metallographic microscope. So that is important. So how do you prepare the specimen, that specimen preparation, and followed by when we complete that specimen, how do you study under the microscope and how do you identify or note the microstructures. That is the first one. Next is about the preparation and study of microstructure, first category, which is pure metal. So you can take any pure metal. We are considering copper, or if you are given like something like pure iron, we can consider. So for the time being, we are considering some of the pure metals like copper. Then we have a copper alloy, which is brass, and copper alloy, other one which is a bronze. So first experiment is on the pure metal, second experiment is copper alloy, third experiment is also on the copper alloy. Then we have other preparation and microstructure of aluminium. Then plain carbon steel. So under plain carbon steel again we have low carbon steel, high carbon steel. Then we have what is called as HSS, which is a high speed steel. And then we have grey cast iron, which is a cast iron category. So up to 8, if you see, all are about either a ferrous metal or a non-ferrous metal, right? So copper, brass, bronze, aluminium comes under non-ferrous, and low carbon, high carbon, and HSS and grey cast iron also comes under ferrous metals. I'll explain what is what and all. But coming to 9th, 10th and 11th, they come under the heat treatment processes. So that is what we do for enhancing the properties. That also we'll come to know slowly. So annealing, normalizing and hardening are the processes. So when we perform annealing, normalizing and hardening also, there will be slight change in the microstructure. That also we'll try to see under the microscope and note the microstructure. Okay. Then coming to the last one, there is a dedicated experiment for understanding the hardenability of a metal. So there is a dedicated experiment called Jomny end quench test. Okay. So as a part of the Jomny end quench test, we are going to study about the hardenability of a metal. Okay? Hardness is different, hardenability is different. We'll come to that part later. Then apart from these 12 experiments, now you can note, I am not counting the first one. It is only to understand or introduction to this lab and how to do what is the basic physics behind and all. That is the first one. So that is the 0th experiment. Then we have 12 experiments. Apart from these 12 experiments, we also have an add-on experiment. That means these are additional experiments which is which will be an inter-lab experiment. That means we will be also using other lab, which is a material testing lab. Okay, so downstairs you also have other lab which is called material testing lab, which you will be studying in the next semester. But we are going to use some of the tools and we are going to find out few of the aspects which is relevant to us. So that is hardenability of steel on the Jomny and benches, and then we also measure hardness measurement of plain carbon steel. So what is the measurement of hardness for a given metal? We are going to examine in that material testing lab. And then we also have, now that we know annealing, normalizing and hardening, they are the heat treatment processes. So when we perform the heat treatment process, there will be some physical change and properties will enhance. So when there is an enhancement, obviously there will be some change in the hardness also. So how much is the increase in the hardness? We are going to compare between the treated and untreated metal. Okay, so that also we are going to do. Okay, so those two add-on experiments we are going to perform additionally. Understood? So these are the list of experiments that you are going to perform. Okay, you can note down later, right? So today we are going to completely understand all the list of experiments that we are going to perform in this lab. Okay, so can you tell me what is this?
Microscope.
Okay, very good. And who can tell me what is this metal?
Steel.
Just have a look. How many of you agree with this? Okay. Yes, aluminium, correct. And so what is this?
Copper.
Very good. This is copper. These two? Brass and bronze. Which one is brass? Which one is bronze? Very good. This one? Very good. Cast iron wrong. Actually, these two you may not be knowing, but you see, this is something to do with cutting. So this is actually a high-speed steel which is used for machining purpose. Okay, so this is in fact both are a drill bit, to be exactly mentioning about the application. They are taken from the drill bit. All right, so it is very difficult to identify and just say which is which metal by looking at its color and maybe to some extent the structure. So it is not, that's not how an engineer will do. Engineers will try to, of course, you can easily, by looking at the weight and also the appearance, it is aluminium, easily we can make out. But what composition and to what extent this can be used for a particular application and all, it is very difficult to just look at the color and make out the difference. So it's not that easy. But yes, I gave a very simple example, and I thought even that was difficult for you, but yes, whatever I gave, you have correctly identified. So now we will understand, suppose if at all I want to study it under this laboratory, can I use this metal directly on the microscope and check? No. So there could be many reasons. First one is it is not compatible enough for loading onto the microscope. So if at all I cut it into a small piece, okay, so if I cut it into a small piece, is this enough?
No, sir.
No. And if at all I want to use this piece into even a smaller piece also, if I cut it, even then it is not. Why?
It is solid. Totally. And it also at one place.
So,
It is not possible.
Not compatible with screws.
but why? Why do you think it is not compatible? Even if I cut into small pieces like this, can I just directly place it under the microscope and view it?
No, sir.
Why not? Huh? Huh? Light source, very good, exactly. So there is a principle, working principle for this microscope. So in the working principle, what you have a light source here, and then you have a pair of prism which will direct it onto the workpiece or the specimen, and then it will be reflected back, and then you can view under the microscope. So by the way, this is a trinocular microscope where you can also have a camera attachment made on the top and two binoculars. So trinocular, that's why it is called trinocular. So you have a pair of lens here, which is a specimen object lens. You can modify as per the resolution that you want, so magnification that you want. So that magnifying factor you need to multiply, and then there are pair of eyepiece. This also gets multiplied, and then you can together this specimen and this object both together will give you the respective magnification number. But again, coming back to the same question, what is the problem? That when the light source is falling onto the specimen, suppose if I take this specimen, you can see it is not flat. There is undulations, which will make the specimen surface reflecting the light not to the eyepiece. It will go somewhere else. So if I keep a specimen which is flat, obviously light will fall and you can see that reflection back through the eyepiece. Suppose if I keep little tilted, what will happen? Light will pass somewhere else, reflect somewhere else. You can't see its image clearly, right? So there are certain rules that you need to follow before keeping on to the microscope. So for that purpose, what we do is, whenever we have a metal for which we need to examine, we make that into a small part. Okay, so we cut it out, and then that metal piece we will make into a specimen. So when I say that into a specimen, so in order to convert that into a specimen, what we do is we have what is called as a bakelite powder. So in the bakelite powder, we will mount using the hydraulic mounting press. So you have a hydraulic mounting press over there. So in that hydraulic mounting press, we keep the known quantity of the bakelite powder, what is prescribed, and then we place this specimen and then keep that powder so that the spaces touches down, and then we heat it and then apply compressive force onto it, so that it gets compacted and it will give you this type of specimen. So this is how we create the specimen. So the small cut pieces are transformed into the specimens. Now the advantage with the specimen is that you can hold it, you can mount it onto the microscope, you can also use it for the pre-processing that we use for which are called as polishing. I am going to explain you about that pre-processing, which is polishing. So for all these purposes, you need to hold the specimen for that pre-processing. So have you all understood how the metal pieces which we want to examine are converted or transformed into a specimen? How are they transformed? By using hydraulic mounting press. So you have a bakelite powder, and first of all you need to place this specimen at the bottom, there is a container there. In that container you need to place this, then you pour the bakelite powder and then you compact it and apply a temperature over it. So there is a heating coil around it, and also you have a hydraulic press which you can compact it. So it will take like roughly 20 minutes or so to get the required strength, and it will transform into this specimen. Okay, so this is the specimen which is comfortable for us to hold it, polish it, use it under the microscope, and then also use for other purposes like etching and other things. So that is how we do it. Okay, any doubts in the specimen preparation? Understood the specimen preparation? We are going to demonstrate that also next. Okay, so this is how we prepare the specimen. Now that we prepare the specimen, any metal which we want to examine in this lab, first we need to have the specimen being prepared. Okay, so that is first thing you need, first step. So the specimen preparation is what we are going to study today after this demonstration, and then next lab onwards, for the sake of time, we will give you those specimens which are already being prepared. Okay, now coming back, next step. So after preparing the specimen, if I keep under the microscope, what I will be able to observe? Microparticles, structures, grain structures straight away. So first thing is, soon after taking out of the hydraulic mounting press, it will be so irregular and it will not be uniform in all aspects. So there is another equipment called belt grinder. So it is nothing but you have a flat surface belt grinder, so that when you position it on the top of that belt grinder and make it to operate, you will get that upper top surface flat. Okay, so that is the first thing after we do the hydraulic mounting press. So belt grinder. So after belt grinder, can we keep under the microscope? Yes, and then what can we observe now this time? Now again structures. So I will explain what is this structure has to do. See, whatever microstructures which we are talking about, it is not visible directly. The reason being, when you understand the microstructure, it basically consists of two things. One is grains, other one is a grain boundary. Okay, so what are these grains and grain boundaries? This we will explain in depth in the class work or classroom, but here what I am going to say is, what is this grains? Grains are nothing but they are likely arranged elements, or what we can say is all the crystal structures which are alike, they combine to form one grain. Okay, how and what we will study there. Okay, as of now you just understand all those atoms which are of same crystal structure are arranged in one grain. Okay, so if I take one grain, they are all having one orientation, and when there is other orientation, it will be in the other side. So they are separated by a boundary that is called grain boundary. So right from the beginning we will understand in the classroom how they are formed from liquid molten metal to a solid, and when it is cooled from hot molten metal, from there how the nuclei is formed, and these nuclei how they grow into a dendrite, and these dendrites further grow into a grain, and last one which is left behind for solidification is nothing but grain boundaries. So during this entire process, grains will first form, and these grains will be randomly forming at several places, and when the temperature is slowly coming to room temperature, these grains will grow, and that's how each oriented grains will be separated into their own areas. Okay, and the last one with lot of impurities which are left behind for last to solidify is nothing but grain boundaries. So you just imagine there are few grains and there is some separations between them which are called as grain boundaries. Okay, so this is how it may appear. Okay, now the interesting thing is, if at all you want to observe these grains and grain boundaries under the microscope, they will not be clear, you cannot observe them under the microscope directly, and that is where we need to do two things. One is to make it mirror finish. Okay, so how do we make it mirror finish? We use what is called as polishing. Okay, so to make it mirror finish, we use polishing technique, and that's how we make a mirror finish. Second thing is, we use what is called as etching technique for bringing out those grains and grain boundaries. Okay, so first thing I'll explain about the making it mirror finish, and the method that we do is polishing. So as a part of polishing, what we do is, we have two things. One is manual polishing, other one is a machine polishing. So manual polishing is done by what is called as, laymen will call it as sandpaper, but these are called as emery paper. These are called as emery papers. Okay, they are not sandpapers, they are emery papers. So hereafter, never ever call them as a sandpaper, call them as a emery paper. And if you notice, these emery papers are having number behind them, and these numbers are ranging from 1200 and 800, then 600. Alright, so we have numbers ranging from 180, 220, 280, 320, 400, 500, 600, 800, 1000, 1200, 1 by 0, 2 by 0, 3 by 0, 4 by 0. So what does this number indicate? What do they tell you? Is nothing but, suppose if I talk about 180 and then I show you 1200, the basic difference between 180 and 1200 paper is, these are having very fine what you call as a granules. So 180 means in a per square inch 180 by 180 division, and the granulars coming out of that when you take, and in the same per square inch if you divide 1200 by 1200, so it is like sieving. You know, for the construction purpose we do sand sieving, right? So they use different sieved sand for different purposes. So when we are using the brick wall and it is not at the finishing stage, then we use a coarse and large granules, sand which are little larger. But when it comes to the finish, then we use very fine, and that's what we do in the sieving, sand sieving. In the same thing, suppose you have that sieve which is having 1200 by 1200 mesh size, and in the same sieve if you have 180 by 180, obviously 180 will have larger grains or smaller grains? Larger grains. And the 1200 by 1200 will have very finer. So that is the number grades which it means. So that is how you have several emery papers numbered in the same sequential order. So you have to collect the emery papers in the same sequential order, starting with the low number to the highest number, and then you have very high finish which is numbered as 1 by 0, 2 by 0, 3 by 0 and 4 by 0. So you have to stack all these emery papers, and then you will be given a glass plate. On top of the glass plate, you take this emery paper, okay, and then so take this emery paper on the top, keep it on the glass plate, and then use this specimen, and you need to position it in such a way that you operate only in one direction. So this we call it as a manual polishing. So in the process of the polishing, what we do is we start from one end and move forward, lift it and then start back again. This is the process that we follow. If you do this way, you are creating scratches. I want to remove the scratches in order to get that mirror finish. So first I need to remove the scratches. So how do I remove the scratches? So start from one end and then move forward and bring back to the first position and then move it. So this is how you need to do. So when you are doing this, I am not rotating. I am keeping only in one direction, and that direction is having perpendicular side larger, deeper scratches. And for example, there is a deeper scratch, like this. That means I am moving perpendicular to the deeper scratches so that these deeper scratches will be gone away, and then all your scratches, if at all they are visible, they will be oriented into one side, that is this. Next paper when I am using, then only I will change again to parallel and I will move perpendicular to that direction. Okay, understood everybody? So what is that? So suppose all my scratches are like this, or let's say like this. What I'll do? I'll move it this way. I'll orient and then I hold. I'll see where my scratches are. Now I can see all the scratches are like upward. So I'll rotate it this way, and then now I'll hold it this, and then I'll move 1, 2, 3. So like that. So I don't have to count. I have to use it as many times as possible. So see that it is all moved, all the deeper scratches are gone away, and then it has made perpendicular. Once you feel the deeper scratches are gone, then you can change the emery paper. Change the emery paper from 180 to 220, 220 to 280, 280 to 320, like that. So you have to climb up the number. Okay. As you move, you will get to remove the first initial stages only. You will be able to remove the deeper scratches. Later on you can't. So you have to spend more time on the lower number. So initially you have to spend more time to remove the deeper scratches. Afterwards you can't. So once this is done, you have 1 by 0, 2 by 0, 3 by 0, where it is more of a very fine finish. Okay. So all these exercise, whatever we are doing, this is a manual polishing we call, and this manual polishing will not give you mirror finish. Will only remove the scratches. Okay. Once these scratches are removed, then we are going to use this polishing machine, which is a machine polishing. So manual polishing is done. Now we are going to use our machine polishing. In that machine polishing, you have a disc. So it is a disc polishing machine. So that disc, on the top of the disc, we are going to use what is called as alumina powder. So there is a slurry. So there is a water mixed with alumina powder, and this will be applied in a frequent intervals, so that while rotating the disc, so there will be a disc which will be rotating. On the top of the disc, we are going to place this scratch free specimen, and then we are going to apply very little amount of force, and we are going to apply that water mixed with alumina powder as a slurry medium between these two. So there is a velvet cloth attached on top of a disc, and we are going to apply this alumina powder mixed to water, and you take this specimen and apply for a little amount of force on top of it. So as a result, you will now see a mirror finish. So you can just imagine, like, this is a mirror, small amount, reflection will be so good. So that is a mirror finish that we are going to get. Okay. Now when you observe under the microscope, what you will see? What will you see under the microscope? Again, structure you will see? No. Why not? This is mirror. What will happen if I keep a mirror below it? It reflects. So you will appear, whatever bright light that is coming on falling onto the specimen, it will be bright light, dark. Okay. So it will be very bright light only can be observed, nothing much. So that is where we are going to use what is called as a etching process. So it is not etching, it is etching. Okay. So etchant. So there is an etchant for ferrous and non-ferrous. Okay. So for ferrous we use nitol, that is nitric acid plus ethyl alcohol, and for non-ferrous we use ammonium persulfite. Okay. So there is a preparation process also involved. You can see that. So nitol is a nitric acid plus ethyl alcohol, and 5% of nitric acid and 95% of ethyl alcohol. So it is very diluted, but still you need to be careful with this solution. So these solutions are prepared and then they will be given to you, and you will also come to know whether it is a ferrous or non-ferrous. Only then you can select the respective etchant. Okay, so these are etchants. So what we need to do? So when these etchants get into contact with grains and grain boundaries, they react differently, because grains are all made of one like composition, but grain boundaries are last to solidify and they have a different composition, and that's where they react differently. So what we do, we take this specimen, okay, after that mirror finish, we place it in a plate containing this etchant for, let's say, the suggested time to react. So it will be very fast, like hardly it will take 10 seconds to react. Excuse me. So for ferrous metals it will take 10 to 12 seconds to react. So you can start the timer for 12 seconds and then you need to immediately dip it in water to stop the reaction. Otherwise what will happen? It will react completely. We don't want it to react completely. We want only to react with the grain boundaries, so that the highlighted things. So see, grain boundaries are separating the grains, right? So when the reaction takes place, earlier it was mirror finish. So when you observe under the microscope, everything appear like a mirror, bright color, that's all, right? But when it is reacting with the etchant, wherever there is a grain boundary, there is a reaction, and that etchant will make a depression. Okay, everything other was earlier it was having very flat, but since it is reacting metal, and that is acid, right? So acid reacts and then metal gets eaten away a small proportion. So you will get a depression over there. So when the light falls on that depression, it will not be bright, it will be dark, like a highlighted sketch outside. So that is what we are going to do, and we don't want that to react furthermore. So we need to stop after just reacting with the grain boundaries. So that's what we do. We keep for 10 to 15 seconds and then stop the reaction by dipping in water, and without touching with any of your fingers, you now place under the microscope. But before placing, you use the hair dryer to dry it out and then place it under the microscope. Now you can observe the microstructure. This entire process you need to repeat in order to see the microstructure. Once you see the microstructure, you can note it down, and we have standard structures for different specimens, and that's how we will identify, and that's what we notify. Understood?
Yes, sir.
Is it clear for all?
Yes, sir.
So I'll explain the next part little bit. Okay. So
What is this black wax?
so this is like a plastic. Now, so when you have this in the powder form, and then under that compressive force and temperature, they form a chain-like structure, and that's what will result in this type of specimen. Okay, so that is what you see here, background, and after hardening, this is the final outcome. This is a specimen. So, like I said, this is how we prepare a specimen, which is very much similar to a plastic thing, but it is through a powder. Okay, so this is more like a hot compaction, and this hot compaction, as a result of the temperature, you get that strong specimen. Now this specimen, you can roughly use it for minor polishing, disc polishing, and even etching. Okay, and you can repeat this process for several times until the specimen gets over. Understood? That is about the specimen. That is about this process. Any doubts? Any more?
So when the
which one? Backward. This will come, but it will not affect anything, because whatever is coming out will go away, and then your main focus will be on the metal. So see, understand, this is a metal and this is something which is a polymer. So obviously this will not create any rupture onto the metal, nor this will be part of any polishing thing. So this is metal. So metal only, try to get a harder thing to get that kind of scratches or any disturbance. So I think that should not be a problem. Inka, any more? Understood?
Yes, sir.
All clear? Okay. Now we'll talk about the other aspects, like first is, have you all understood the purpose of etching?
No, sir.
No. Very good. So what is this etching has to do? See, when I say, suppose if you have any rough? Alright, let's say I have I am talking about the grains and grain boundaries, right? So let us say, like, this is the specimen which we are talking about, and not this entire black one, but I am talking about the metal specimen when you see under the microscope. So that microscopic view I am talking about. Okay, so when we observe under the microscope, first thing is we are trying to understand the physics behind it. Only then we can appreciate. So the physics is like, it is cooled from a liquid molten stage to room temperature. So when it is cooled from liquid molten stage, obviously how the liquid molten stage will be very hot, and that makes atoms very rapidly moving and fastly moving here and there, right? So at that random moment, none of the atoms will be stable. They will be very energetic in moving here and there, and it will create lot of disturbance, and that is also possibly the reason why that kinetic energy is so high. So let us say, this is the liquid stage where my atoms are, randomly arranged and randomly moving here and there. But slowly when it starts cooling down, what will happen? As the temperature cools down or temperature is coming down, there will be some stability. So that movement of atoms will slowly come down, isn't it? So when it comes down, they will start forming what is called as nuclei. So at some places, it starts forming a nuclei, which is nothing but all the like atoms will come closer to each other, and this becomes the center for further cooling and further joining the neighboring atoms. That's how the nuclei is formed. And they all try to orient in one direction. And that's how a dendrite is formed. I'll try to show you in the PPT later. So after forming the nuclei, it will try to grow like a tree-like structure, which is leaf-like a structure, or dendrites are like broken needles and snowflakes, more like a snowflakes. So these dendrites are nothing but, they are all collection of atoms which are like, and they are growing in particular direction. Now as temperature cools down further and further, there will be many such nuclei growing towards the dendrites. So there will be many places where there will be nuclei and there will be growth in the form of a dendrite, right? And furthermore, as there is a stability, there will be more and more such nuclei, there will be more and more dendrites formation, there will be more such stability which gets into the atoms. Okay, so this is how first stage of nuclei to dendrite formation. But still there is a liquid. That means still the temperature is very hot, and everything will slowly transform into a dendrite. And these dendrites are like, like I said, tree-like structure, like something like this. That means there will be some branches, and in between the branches there is still a liquid. And further cooling will do what? even this liquid which is present in between these branches also cools down, isn't it? And then leaving behind something like this, isn't it? That means you still have some liquid which separates out. But what about this formed dendrite? It is having one uniform structure, and now they are no more called as dendrite because it is no more a tree-like a structure. The in-between liquid also solidified and it has formed one single entity called grains. And whatever is left out from one grain to other grain in between, like a boundary, is the last thing to solidify, and that's what we call it as a grain boundary. So remember, grain boundaries are the last to solidify, and from one grain to other grain it only differs in its orientation. Rest of the all properties are same. So that is the reason why we indicate with hashes which are alike, not similar to any of this. So finally, when we observe, it will be something like this, in which all the grains are oriented in one direction, and these grains are separated from one another by a boundary. We call that as a grain boundary. So this will become the grain boundary, and this becomes the grains. So you have many grains separated by a boundary. Okay, and very important thing to notice here is grains, all the grains are same, with same properties, same composition. Only difference is orientations are different. That is why I am hatching it in a different direction. Whereas grain boundaries, they have totally different composition compared to grains. They are very rich in some composition. So that is the reason why they are not able to solidify at a time, and they are left behind with all the impurities, and finally at the end they solidify, taking all the impurities into picture. And that's the reason why you have little different composition. Energy levels are also different, and that is the reason why when we expose this type of metal, of course this we can't see under the mirror finish. So we are able to achieve till the mirror finish, right? So when we want these things to appear, they are still there, but we can't see it through the microscope because they appear everything uniformly under the microscope. That is the reason why we use these etchants to react with the grain boundaries. So some etchants will react with the grain boundaries, some will react with the grains itself, and that is the reason why the timing is also different, and that is the reason why you need to precisely maintain the time, and during which the reaction is completed, and you need to stop the reaction by dipping in water, and only then see, for example, this nitol, it will react with the grain boundaries, because of which if I take the cross section earlier, if this is the specimen, everything will be flat and everything will be uniformly bright and all. But whenever you expose it under the microscope, there will be a reaction which is very small, but even then that light will go here and reflect here, and it comes back on the other side, making it darker portion. And that is the reason why all the grain boundaries where their reaction occurred, that will be darker in color. Rest of the things will be bright in color, and that is what you can identify as a microstructure representing the grains and grain boundaries. Now is it clear? Understood?
Yes.
Clearly?
Yes.
What is a grain? What is a grain boundary? I will explain about the grain formation even further in the classroom, about its existence, how it forms, how it all the like elements forms, and what is the physics behind that, kinetic energy, potential energy with that, and all those things, their stability aspects, how the count stability, that number of atoms count stability. So all those things we'll discuss in the class in detail. But for this lab, I think this should be good enough to understanding why do we use this etchant at all. Why can't we directly see under the microscope? So none of the metals you can see directly. There is a etchant for even stone like marble, granite, and that's how you characterize and that's how you observe. Clear? So finally, to conclude, in this lab, what do we have? Now if you observe altogether, how many microscopes are there? 5 microscopes. Okay, you have 5 microscopes. Among the 5 microscopes, there are 2 are trinocular and 3 are binocular microscope. So the trinocular microscope is having 25x to 1000x magnification, whereas the binocular has got 25x to 450x only. So object length is little different there. That is one thing, and of course you have trinocular, this portion which will help us to fit the camera attachment. Okay, so that is about the trinocular binocular microscopes. So 5 microscopes. Then you have the one hydraulic mounting press. Only one hydraulic mounting press. Then you have a belt grinder, right? One belt grinder. One polishing machine, disc polishing machine. Then for the processing, we also have what is called as a muffled furnace. Okay, this will be used for the heat treatment process, about that annealing, normalizing, hardening and all. We use this furnace here. Okay, so the furnace helps us to heat to that required temperature. Okay, so there is a furnace available, and you also have what is called as Germany end quench test. And this Germany end quench test is a experimental procedure in order to find out the hardenability of a specimen. Okay, understood? So altogether you have 5 microscopes, one belt hydraulic mounting press, one belt grinder, one disc polishing machine, one muffle furnace, and one hydraulic Germany end quench test. And apart from this, we also going to use material testing laboratory equipment which is used for hardness measurement on these specimens for both treated, non-treated, plain carbon, high carbon, just to understand what is the hardness value variation before treatment, after treatment. Clear? Understood with all the processes? Yes. Now I'll share the manual to you today, and in that manual all these experiments will be there. And the first experiment, which is a 0th experiment about the metallurgical microscope, specimen preparation and an introduction. In that you have a table which will help you understand which etchant to use for which type of metals. We are only looking for few metals in this lab, but there is a complete picture about all the metals and their respective etchants to be used. Okay. Similarly, you need to draw the microscope in order to understand that constructional schematic diagram you need to draw in order to understand the working principle of it, how to use and all. Only this microscope and that table. Then coming to all the experiments where you identify the microstructure, you need to draw a circle, and once this entire process is completed, you observe under the microscope and draw that in the microstructure in your observation book, get it signed by the faculty, and only then reproduce in the record sheets. Okay, so here we are going to have record sheets, individual record sheets. That template also I am going to share, and only with the index sheet I can sign and give the dating there itself. So since you are coming today, after next week you will go to FM lab, and that next week you will come back here. So by that next week, when you are coming back to this lab, you need to come with your introduction. Okay, understood? And the main important things to remember, do's and don'ts in this lab are, one is apron, shoes. That any lab you go, these things are mandatory. Apart from that, careful usage of microscope, etchants, even though they are very much diluted, you cannot rub your eyes by using those etchants, or nor use anything other than that for harmful this thing. So whenever you have used this etchant, try to be very careful with your eyes and sensitive parts like finger, toe tips, or wherever you have any cuts. So be careful with that. Then while using the furnace and the geometry and quench test, you should be at most careful because they are working under high temperatures, high current also. So these two you need to be careful in those aspects. Clear?
Yes.
And in terms of coming to the evaluation process, like I said, in the laboratory it will be day-to-day evaluation, meaning on daily basis you will be evaluated on both the aspects, on how you perform the experiment and also how you are responding to the questions that we ask, viva questions that we ask, and day-to-day marks will be there. That 15 marks day-to-day evaluation will be taken as an average. Okay, so every lab day-to-day experiment counts. Timely submission of record counts. If you are not submitting record on time, there will be some minus marks. Okay? Understood?
Yes, sir.
So any doubts? All clear?
Yes, sir.
So till the end of this semester, we'll be having the same rules, same things, and I hope you will follow all the rules to get full marks in the laboratory. So lab, we will give full marks provided you maintain all the necessary things that I mentioned just now. Is it clear? So Moodles will post this video and also will post all the material that is needed. Try accessing through the Moodles itself. If you are facing any difficulty, let us know. Clear?
Yes.
Okay. So while performing, we will try to see if there is any issues. But otherwise, that's it for now. Thank you.